Welcome to the second video in this Sphero coding series. In level 1, we talked a lot about just the basics of the way that the Sphero Bolt works. And then this video, we're going to kind of go through the sensors and talk about how you can first understand what the sensors are actually telling you, and then just a little bit talking about how we can use the sensors to both extract sensor data that might be helpful, and then also use those sensors to make our bolt do certain things that we want it to do. So let's get started. So the first one that we're going to talk about is the accelerometer. What an accelerometer does generally, it measures the rate of change in velocity. That's what the acceleration is. And for the bolt, it measures the bolt's rate of change in velocity. And it does that along 3 different dimensions. So we're going to talk a little bit of geometry right here. There's different options that you have, as you can see here, that you can pull up for the accelerometer. The accelerometer, when it gives you data, it's in G's, and that's equivalent to like 1 G is the gravity that you're experiencing right now, the acceleration due to gravity, which is 9.8 meters per second squared. And so when you get a readout, if the readout is like 2, that tells you that in a certain direction, the bolt is experiencing an acceleration that's twice the acceleration due to gravity. So there's 3 different axes, 3-dimensional space, of course, where we can experience acceleration, or the bolt can experience acceleration. The first one is along the x-axis, and that's just a left to right. So if it's going to the right, that's positive, and if it's going to the left, if it experiences acceleration to the left, that would be showing up as negative. The y direction is kind of the forward and back. And so in this one, forward is this way. And remember, we know which way is forward because before we even start anything else, we orient ourselves with what they call that tail light. And that's how we know, because this thing is a sphere, we know which way is forward. So if it's experiencing acceleration forward, it's going to end up being a plus in the y direction. And if it's accelerating backward, it would show up as negative. And then the z-axis, that is based off of kind of this platform, or like the inner part of the bot. And it's just going to be perpendicular to the surface of right here, this LED matrix. And so for the z, if it's going kind of like perpendicular up from the matrix, then that's going to be considered positive. And if it's going like down from the matrix, that's going to be negative. There's one more option that they give you right here, which is vertical. And so the bolt can tell based on its orientation which way is up based on the gravity of the Earth. And so if you want to know vertical acceleration, that will use kind of some other sensor magic and let you know acceleration in the vertical direction. And so for the vertical, this would be plus is going up, and then vertical, if it's accelerating down, it would be negative. And so that's just a nuanced difference between the z and vertical, because this LED matrix might not always be pointed kind of flat on the surface. And so if it's tilted, you could use the vertical component of the accelerometer to give you a little bit better information about up and down acceleration. The bolt also, like I just said, knows its orientation in space. It knows which way it's pointing, which I put in quotes because, of course, it's a sphere. So we have to define some of that stuff. But there's 3 different kind of axes, and we talk about them in terms of pitch and roll and yaw. And I'm going to explain each of those individually so we have kind of a good sense of what that actually means. I like airplanes. I like airplanes and like GMC Suburbans and Yukons and stuff. Those are the things that machines I'm interested in. But with planes, roll and pitch and yaw are different ways that a plane can move through space. So I'm going to use examples there. For those of you who are probably not so familiar with planes, it might be helpful to think of this kind of weird disembodied head here, and think about the way that you would move your head to get these different things. So pitch, if you think about it, it's like changing the pitch of your head is either like looking down or looking up, like this guy is right here. Roll would be like tilting your head to the side, to the right or to the left. And then yaw is like turning your head. So keeping kind of your eyes on the level, but turning your head to the left or to the right, that would be considered yaw. So if that kind of analogy or that type of orientation helps you, that's a good thing. So let's talk individually. First is pitch. So you can see here I'm moving the bolt along different pitches. And so it tells you essentially how much forward or back it's tipping. And so I think when I think of this, I think like the pitch of a roof, or like steepness of roof. And that helps me remember what pitch is referring to, because when I was right after my freshman year of college, I briefly worked for a roofer, and they liked me because I could carry a lot of shingles up onto the roof with a ladder, and they didn't like me so much because we would work on these really dangerous jobs and be like, hey, if we're working on a 3-story building, like, should we have safety equipment? And so when you ask questions like that, at least for the person I was working for, I didn't maintain my employment super long there. So, but that helps. If that helps you remember pitch, like the pitch of a roof, that's a good thing. So this is going to vary from negative 180 to positive 180. If it's positive 180, that means it's tipped forward 180 degrees, so that this LED matrix would be like facing forward. And if it's negative 180, it would be facing all the way backward. The matrix would be facing all the way backward. Roll is another one that's, you can see here I'm demonstrating the roll, which is just kind of side to side orientation, either tipping to the left or to the right. And because I'm a child of the 90s, I can't think of roll without thinking of some Peppy here, this rabbit telling me to do a barrel roll in Star Fox. If anybody played N64, I don't know. But that helps me remember it. As you can see, this computer kind of craft is rolling. It's turning side to side and avoiding laser fire as a result, of course. And then if you are more traditional and you want to think about the way roll works, just think of a plane. When a plane makes kind of a normal turn, a big component of it is roll. Turns to the left and to the right, or banks that way. So that's what roll is. And it varies from plus 90 to negative 90. So on the positive side, if it goes to the right, that would be considered right there. I'll try writing that again. If it goes to the right, it's going to have a positive value. If you instead kind of roll it to the left, and this would be a side-to-side movement, or tilting, I should say. Tilt. If you go to the left, then it's going to have a negative on it. So that's what the roll is about. Yaw is kind of the spin. So you think of like just keeping your head on the level, but turning either to the left to look at something or to the right to look at something. And so I think, and I remember what yaw is based on some of the scariest experiences I've ever had on commercial flights, where you're landing, but there's a really strong crosswind. Maybe you guys have experienced this, maybe not. But it looks, as you're landing, it looks like you're not like lined up on the runway, and that's on purpose, because you have to fly at an angle into the wind in order to kind of maintain your direction. And then at the very last second, the pilot uses the rudder and yaw, like does a yaw turn to move the aircraft online with the runway, because of course you can't land at an angle, because the wheels, once they catch, you go off the runway. So that's kind of how I remember what yaw is about. It's this kind of rotation, or like turning your head. You could think of it that way too. And so this is also a negative 180 to positive 180 degrees based on your turn. There also are gyroscopes on board on the Bolt, which is fancy. They're electronic gyroscopes. But basically, these are sensors that measure the rate of spin. This thing is a ball, and so it can spin. And so there might be a time when you want to know, like, how fast is it spinning? And there's a sensor for that. And so just like for orientation, there are 3 different kind of axes and different names that we can think about when we're talking about how fast it's spinning. And they line up with what we talked about with orientation. It's important to know that this is measured in degrees per second. So if you get a number, well, we'll have an example here in a second, but first we'll talk about the axes here. So for the X, this is pitch, all right? And so if you are moving forward, like rolling like this, rolling forward around this axis, that would be positive. So forward is positive in that one. If you're on the y-axis and you're rolling as a right way right here, rolling to the right, that is positive around this axis here. And the one that's most likely to be of use to you is the z-axis, because if you go around counterclockwise, that is positive. And just because of where most of the weight is in the bolt, most of the gyroscope measurement that you'll need or that'll be useful will be related to the yaw. The robot, because of this ballast weight, doesn't really like to spin forward or sideways. It likes to do kind of yaw spins. And so as an example, you might ask it to give you a roll gyroscope reading, and it gives you a reading of 360. What does that actually mean if it gives you a roll gyroscope of 360? Well, what it means is that you are getting positive 360 degrees of rotation per second. And of course, 360 degrees would be like one full rotation per second. All right, and if we're talking about the Y, that means that it is kind of rotating around like this once every second. It would be an unlikely thing to get. It would be tough to get that, again, because of this ballast weight on the bottom. Kind of throws that kind of stuff off, but it's possible. You can make it happen. So that's what that would mean. Let's talk about velocity here, because there is a way to find out the velocity from your bolt. It's just going to measure how fast the bolt is going, and there is a little bit of an asterisk here, so we'll come back to that. But for right now, you can find out the total velocity. You can find out the velocity of just the x-axis or just the y-axis. And so the way that we do this is, first, it's measured in centimeters per second, and that's important to know, because if you're going to use this number for anything important, you're going to want to know what the unit is. It won't give you the unit if it's reporting it automatically. So if we think about the bolt here with its tail light pointed at you, all right, and I put it on this this is a top-down view, and I put it on this grid here. If you want to know, if you ask for the x-axis, it's going to give you your lateral speed. And that's side-to-side speed. So how fast is it going this way? It would give you a positive speed. If it's going to the left, it would give you a negative speed in this plane. You can also, and remember, this is a top-down view here, so we're looking like down on the bolt. You can get a y-axis speed as well. So you can, if it's going forward, this would be plus y, just the same way that it works on a coordinate plane like this. And if it's coming back towards you, because that's backwards, you get negative y. And then kind of a fun thing is that you can also get the total, and it'll compute it for you, which is kind of nice. And so it doesn't matter what direction it's going in. It could be this way, this way, this way. But it will take its y speed and its x speed and then compute for you the combined vector. And so that's where you get the total velocity. But it doesn't matter which direction it's going. The total velocity is always positive. All right, so you'll never get a negative total velocity. It doesn't care about direction when it's computing that. So now for the asterisk. So a bolt measures its speed based on motor movement. And anyone who's used bolts before knows that the motor movement, actually what's going on inside the bolt, doesn't always match up with how fast the bolt is going in the real world. And the reason for it is related to the fact that it doesn't always get the best traction. So if you were like this person who was stuck for a moment and the wheels were spinning on your car, but you weren't moving, your speedometer, the inside of your car, if you were looking at it, it might tell you you're going 25 miles an hour. But of course, if you look on the outside of the car, you see that while the wheels might be going like they're going 25 miles an hour, the actual car is going nowhere until the end of that GIF. All right, and so this is a really good analogy for the bolt, because sometimes the bolt will tell you that it's going, oh yeah, I'm going like 50 centimeters per second. But in actuality, it's not going anywhere near that because it is slipping on the surface. Maybe it's going up a ramp or something. And so the velocity that it gives you is not always the real world velocity. So that's something to be aware of if you're trying to make calculations about how far it's going to go and things like that. Similar asterisks will be involved in some of these other ones that rely on the same thing. So you can also figure out the location, and so you can call up location information, sensor information, and this is just going to measure how far the bolt is from where it started. Okay, so we think of it on this coordinate plane. You can get the total location number, you can get just the x-axis, which again is going to be in this top-down view, positive, negative, just like it would be on the coordinate plane. And here's the positive and the negative on the y. It's measured in centimeters, so that's important to know the unit. And then, like I said here, the x-axis, if it's going to the right, it's going to be positive. And for the y-axis, if it's gone kind of away from you, so what's what we call forward, it's going to have a positive term there. And the total, if you want to know total location, that's how far away it is from its origin point, but it doesn't care about the negative or the positive. So if you were like, if it gave you, if you took your bolt here, or took your bolt here, or took your bolt here, or took your bolt here, it wouldn't matter because all of these lines are the same. And so that total value it would give you would be the same regardless. Okay, so that's something to know, that it's always a positive value, and it just tells you how far away your bolt is from that origin point. Again, it makes this calculation based on motor movement. So if there's any slipping or anything kind of off about that, it'll be recorded in that. So this doesn't always match up with what you see in the real world. Your bolt can also give you the distance, the total distance that it's traveled up to any point in the program. This differs a little bit from the location because it doesn't care how far the bolt is from the origin point. All it cares about is how far it's traveled. This is going to be measured in centimeters, just like location is. But again, it doesn't care kind of how far it is from this origin point. So for example, you could have something where the distance traveled is 20, but its total location value might only be 2. And so how is this possible? Well, if you think about the distance traveled, maybe it goes 4 this way, 5, 9, and it just goes all around, and then eventually it ends up over here. Well, the total distance it's traveled is 20, but its total location, basically its distance from where it started, might only be 2. So there are 2 different things that are involved there. Okay, so distance is not exactly the same thing as location. And just like we've been talking about before, the bolt determines distance and location and velocity using motor movement. So if there's any slippage at all, or for any reason it doesn't, like there's anything, the motor movement does not necessarily say exactly how far it's gone. It estimates it. Okay, so in terms of speed, the speed measures the target speed of the bolt. And what does that mean? It basically tells you what the speed is set at. What is it set at? And this is based on just the programming of what's been used to tell the bolt how fast to go. And I just call these SSUs, Sphero speed units, because they are not any sort of like centimeters per second or anything like that, but there is a helpful conversion factor that I found through experimentation that 100 Sphero speed units, or SSU as I call them, is about equal to 40 centimeters per second. And that's in kind of ideal conditions where the Sphero is getting good traction. It can do cool stuff like break through walls. Who knew? All right, and so the heading. This is just a report of the current heading that the robot has. You'll set it at the very beginning as long as you set the tail light towards you. The tail light, as long as that is kind of aiming at you, that's that blue thing that you set at the beginning. Hard to see there a little bit. But as long as you set it, it's going to be 0 degrees when it starts. But through the program, it might turn based on the commands that are in the program. And so you can use this sensor of heading to figure out which way it's pointing. And this shows you how many degrees, what it would report if it was pointing in any direction other than straight away from you, which would be 0 degrees. Pointing at you would be 180. If it's pointing to the right, it'd be 90. Pointing to the left, it would be 270. Time elapsed. You can figure out how long the program has been running and use that, and that's measured in seconds. So those numbers can get kind of big if you have a program that runs for a while. But there's some good reasons why you might want to use this. Ways that I've used it in the past is for time-based triggers. So there's times when I want the bolt to do something, but I don't want it to do it immediately when I turn the program on. Maybe I want to position the bolt or get things ready, and so I put a delay on it. So I say like after such and such time has elapsed, maybe 30 seconds, then do something. All right, so that's one way that you can use it. And you can also use it for an automatic shutdown of the program. There's an exit program block, and you can use the time to check and be like, okay, it's been running for 5 minutes. Now I want it to automatically turn off. So there's just a couple ways that you could potentially use the time elapsed function. All right, compass direction. So this is going to first calibrate compass. There's a block that's for calibrate compass, like was talked about in the previous presentation. But it's going to use whatever calibration that was to estimate its current real-world heading. And so it bases it off of north. Everything's based off of north, or the calibration. It uses the Earth's magnetic field, hopefully. Earth's magnetic field to do this. In my experience, it is very prone to interference. So where you might have like a normal compass, it's not really super affected when it's inside by any other kind of metallic objects or other things. This one very much is affected by anything. And so I would be careful in using this. I have not had great results with this. I get very inconsistent kind of directions when I try to use compass direction. But it is, if you don't have interference, it would be a really good way to make sure that if you want your bolt to go a certain place and the initial orientation can't be guaranteed, if you know the direction, you might be able to get it there using the compass direction. And this is measured in degrees. All right, the luminosity sensor. This is a cool one. So the luminosity sensor tells us how bright the light is that the bolt is experiencing. And it has a sensor that does this. And so in this GIF, it shows you where it is. It's in the front right here. That shows you the ambient light sensor. It's in the front, right by the front LED. And you can see it right here. And so if you are aiming, if the bolt is aiming towards you, then it's going to be in the front there. And of course, just for orientation's sake, here is where that tail light is. So if you have the tail light pointing at you, then the ambient light sensor is going to be on the other side. It measures in something called lux. This is a unit of brightness of light, where 0 would be like complete darkness. And there's different estimates on this, but like direct sunlight would probably be somewhere in the 100,000 range. It gives you an idea of kind of the range of lux. So the question is like, how do we use these things? So far, I've showed you all these sensor things, but if you guys have played around with the block coding, you know that these sensor deals by themselves can only be inserted into other blocks that have kind of these circle-shaped areas. And so in this application here, this would be a little bit weird, but kind of cool. What would happen here, this back LED, this block controls its brightness of that back LED. And so what this would do, this would use however fast the bolt has been told to go to control the brightness. So this would make like the faster, the brighter we would see that back LED. which would be kind of cool. But this just shows you that, like a sensor can't be used by itself. It has to be, put into something. So the first method of getting sensor information out, if you're doing some kind of science application, is to look at the graphs either during or after the program runs. And the way that you do this is you select these three dots after it runs, and then you go to where it says sensor data, and then it's going to pull up these graphs, and you can look and see it tells you location, orientation, gyroscope. You can get a decent amount, accelerometer, velocity, decent amount of information comes out of those graphs, and you can just look at them that way. So again, you click here, you click on sensor data, and then it pulls up the graphs for you. A second way that you can do this, to get a little bit more advanced, is you can actually download a CSV file. This is like a spreadsheet file that you could look at in Excel if you want the specific numbers rather than just kind of the visual graph data. Start like this again. We click here on those three vertical dots. Then that opens up this little dialog menu here, and you click on sensor data. And then it pulls up the sensor data screen, and then you tell it you want to download that CSV file. And then from there, you can check mark the ones you want. So these are all the options. We want accelerometer, orientation, distance, gyroscope, location, and velocity. We could say we want all of them. And so then it's going to package that up into a nice CSV file. And then you can, once you've decided on that, you can export that using, of course, that kind of share button to whatever you want. So you can put it on Google Drive or somewhere else that you can use to look at it on a computer or on the mobile device itself. A third way to do it is to use strings to actually get the bolt to actually talk to you, or to display sensor data. And so this short bit here kind of explains how that works.
So the first thing that we need to do is find the operator build string. You can see there's kind of a square shape right here. So right now, even if we tried to, we would not be able to put the luminosity sensor data directly in there. And so we need to modify this string. And so you click this edit button, and it pulls up the build string. You can add things that are numbers, or strings are basically just like text or booleans and colors, which we're not going to talk about right now. But if we want to add the sensor data for luminosity, we need a number in there, and we can actually drag this and change the order of what we have in here. So I have a number first, and then a string, which is just text. And so once I have that, I can click that check mark. And now you see I have an oval thing right here, and then I have this square, which will be where we can put text. So to build this string, I can take the luminosity sensor data, put it in there. Then I can just click on this right here and type in lux. And so it'll give us the number for the lux that the sensor, the ambient light sensor, reads from the bolt, and then it has also the word lux to tell us what the unit is. And so we can have, on startup then, we can have the Sphero Bolt tell us by speaking this string out, can tell us what the lux is. So we put the speak block in here, we've built the string that's first going to report the sensor data, and then it's going to use this text to say lux on it. So it's going to say whatever the number is, and then lux. And then we can also use scrolling text to see it on the matrix display. So what we'll do here is just duplicate this string that we've built already and drop it into this square shaped deal within the scrolling text block. And so now what's going to happen, after it's spoken the luminosity, it's going to show it on the matrix display, the number and then the word lux in this kind of blue color at 15 frames per second, and then it's going to wait. So that is really quickly how you can use strings and sensor data to report out both spoken and as scrolling text on your matrix some of the numbers or sensor data that you might want to extract.
So then as a final deal here, how to use sensor data actually in your programs to make something happen. There's something called nitroglycerin that you guys may or may not be familiar with. It was developed in the 19th century as an explosive, super explosive, to the point it's a liquid, a clear liquid, that if it's shook too much, it will explode. It decomposes and explodes violently. It's one of the most powerful explosives, conventional explosives we have. And then eventually it was figured out by a guy named Nobel how to use sawdust and a couple other things to turn it into dynamite, which was stable. But nitroglycerin itself was not stable. If you shook it, it could explode. So I wrote a program called Don't Shake the Nitroglycerin. And this uses some accelerometer data well, let me show you how it works.
Stay steady, stay steady. Careful, don't want it to explode. Careful, don't want it to explode.
Oh, it exploded. All right, so that basically simulates what would happen if you had nitroglycerin in your hand, like a bottle like this, and you decided to not be careful, as the computer voice told us to be. And this is kind of the program. This is all it took to make that happen. So the first thing that I did here is I turned stability off. This keeps the bolt from adjusting to movement. Because if you don't do this, it will kind of move interior as you move the ball around. It'll try to keep this LED matrix kind of facing up. And so I turned that off. Then I started a loop. A loop is just some repeated code. It's going to kind of go through this code. Once it's done going through that code, it's going to go back to the top and it's going to do it again. And I have it set up to loop forever. So until I turn this off or until a command turns it off, it's going. So then I have an if-then statement, which was talked about in the previous video. I said if the total accelerometer, and so this is the sensor data, it's checking to see, like how much acceleration there is actually in the bolt. If it's less than 1.1 Gs, then turn the screen green and say stay steady. All right. And at that point, it will go back to the top and restart the loop and check again. Okay, let's say that accelerometer value is above that 1.1. Now it's going to go to the else part and come down to this next if-then statement. This is nested, a nested if-then statement that we have right here. Okay, so now I'm telling the bolt, check the total accelerometer, and if it's less than 1.5, we've already established it's greater than 1.1, but if it's less than 1.5, so between 1.1 and 1.5, show it in yellow and say, careful, don't want it to explode. All right, then it goes back to the top and runs the loop again. All right, then if as it's running through, let's say I've done what I did in this little video and really started to shake it, it goes and it checks, and now the total accelerometer is like 2 or something like that. It checks to see if it's less than 1.1. It's not. So it goes to the else. It checks to see if it's less than 1.5. It's not. So then it goes down to this else statement, and it does this matrix animation that I pulled out of the EDU app, which says it shows like a little explosion in light because I shook it too hard, and then it plays the sound effect of an explosion because I blew up the nitroglycerin. And then I have this command down here to exit the program, and that just shuts it down. So that's just one way, just a fun little program that doesn't contain a lot of blocks that makes use of the sensor data to do something. In this case, check to see how hard you're shaking the bolt and see if you would explode the simulated nitroglycerin. So this video has gone through all the different sensors that you might need to use. It's talked about how to extract some of the sensor data, and then finally it's just given a very brief introduction and an example of how you might use the sensor data actually within the code of your program to do something.